So let us now talk about Serre spectral sequence. So Serre spectral sequence applies to fibrations. So say we are given a fibration like this. Our base space is B, fiber is F, and this is the space X. So this base space B we take as a connected CW complex so that it comes with the natural filtration. So the idea is that we are actually trying to work with space X, and this space X inherits its filtration from the base space B. So if you put a filtration of space X, try to compute its spectral sequence, then you know that page infinity will give us the homology groups of space X. And these homology groups precisely lie on the anti-diagonal. So this we have talked about before. So this we already know. Now Serre spectral sequence actually gives us page 2 of the sequence so that we can play page 2 with page infinity and get some interesting results. So Serre spectral sequence says that the page 2 will look like HP of this base space tensor with HQ of F. So the entry in the position PQ is tensor product of homology of the base space with the homology of the fiber. So this looks almost like, if the space X was given to us as B times F, and then you can use the Kunath formula. But by the Kunath formula you will also have a Tor term. But we make appropriate assumptions so that this Tor term in the Kunath formula is 0. So this Tor terms become 0. So the only thing we are left with is this. So space X is almost B times F. So this is all what a Serre spectral sequence is about. But we are going to do a special application, a Gysin sequence, so the inner workings are clear. So in some sense this Serre spectral sequence is kind of obvious to us because if you take appropriate coefficients like either in fields or assume torsion free coefficients, then most likely you're just going to get this tensor product and your Tor term is going to be 0. So as I said before, the base space, our base space B, this is taken to be a CW complex with a natural filtration. So let us see what page 0 would be. So page 0, you just take tensor product of base space with the fiber. So this is page 0. So page 0, this is it, but what are the arrows on page 0? So notice that our formula is minus R and R minus 1. So on page 0, this is 0 minus 1. So the arrows are going 1 down. So the arrows are going 1 down. You have something like this, CP tensor CQ in the column, and then the arrow goes like this, CP tensor with CQ minus 1, and so on. So column is the same. This Q is changing, the row is changing. So you can take homology with respect to here, and you can come to page 1. You get HQ of F tensor with CP of P. So now on page 1, you plug in here, you get minus 1, 0. So you're going 1 towards the left. So arrow goes 1 left. Now your row is constant and this is changing. So you have CP tensor with HQ, arrow is going 1 left. So this is coming from CP minus 1 tensor HQ and so on. So now you take homology with respect to the CP and then you get HP on page 2. That's how you get this. So this is kind of hand wavy. To see the exact proof, you have to see spectral sequences by Hatcher. So this CPB, because B is a CW complex, has cellular homology, and we know that if it has cellular homology, this pth part is actually nothing but a homology group, HP BP comma BP minus 1. So this is obviously given again in Hatcher. This is on page 139 of Hatcher's algebraic topology. So let us now see a application of Serre spectral sequence. So now we talk about the Gysin sequence. So now we take the fiber as SK. So this you take as SK. So if you take it as SK, then you know HQ of SK is integers only for Q equals to 0 or K, and otherwise it is 0. So this HQ of F now becomes HQ of SK. This is integers only for 0 and K. So if you just put integers here, your tensor with integers, you will just get HP of P, and otherwise it is 0. So this second page has 0 otherwise. So this is PQ. P is the column number, Q is the row number. So you have only two non-zero rows. So the 0th row and the kth row are non-zero. Everywhere else on page 2 you just have 0 sitting. So first notice that the action will begin on page k plus 1, because you have this arrows going r minus r to r minus 1. So on page k plus 1 is the arrow will go minus k minus 1 and then k, because you have to go from 0th row to kth row to have non-trivial arrows. So say this is row 0 on our page 2, this is row k, this is our page 2. So these are the only non-trivial rows. Everywhere above and below these rows you just have zeros, so you can't do anything about it. So the problem is that say you take something on row 0, there is an arrow going out of it and there is an arrow coming into it. So the arrow coming into it always comes from 0. An arrow going out of it could land in 0 or could land in row k. So if it lands in 0, then there is no action, because you take any module, 0 going in and then 0 going in, 0 coming out, take its homology, it is still M. So page 3 will again look like this same page, and so on till this any arrow here reaches here. So if this object here does not get mapped to this object here and instead gets mapped to 0, then you have nothing to do. Keep taking its homology, is the same thing. So homology of this is the same thing as M. So take its homology, you will just get the same complex. So for any action, for any relevant action to take place, the arrow from here has to reach here, but this distance is k, and so you have to have, so this is column and this is row, so you have to move k up from current position, and you can move k up only if you take r as k plus 1. So r as k plus 1 means action is on page k plus 1. So action begins on page k plus 1. Before that you just have stability. So where the arrow will go k plus 1 left, that is minus k minus 1, and k up. It will go from here to here. So before page k plus 1 everything is the same. Then you take homology on page k plus 1. So here you will take homology. So this is now page k plus 1 where arrow is going from here to here. You take its homology, and then after that you will put homology exactly at the same position. Now on page k plus 2 the arrows are longer. The arrows will no longer go from here to here. They will overshoot it. So if you are working on page k plus 2 now, so say you are on page k plus 2, then you have non-zero objects at the same position, because once you take the homology at the same position, but the arrows will overshoot. They will go above this row, and therefore they will again stabilize. So after page k plus 2 you again have stability, because the arrows are really long. So ek plus 2 is equal to ek plus 3 all the way to page e infinity. So the only action you have is on page k plus 1. So let us rewrite page k plus 1. So first notice again the entries stop changing from page 2. So page 2, page 3 all the way to page k plus 1, they have the same entries, but on k plus 1 you have a long arrow. So on page k plus 1 you have this arrow going from e2 n0 to e2 n minus k minus 1 k. So obviously you're going minus k minus 1, that is k plus 1 left and k up. So this is the bi-degree which you add here and here. So again notice that I'm talking about page k plus 1, but we are writing e2 here. Instead of 2 you can again write k plus 1. It doesn't really matter, because the entries are the same till k plus 1. So we are working in page k plus 1, but we already have this formula for e2, and this formula for page 2 was hn and hn minus k minus 1 b. So we know that these are the only non-zero entries live in row 0 and they live in row k. So row 0 is this row and row k is this row. So this is where the non-zero entries live. And as we have seen before, here you will get hn b, and here you will get this entry is hn minus k minus 1b. So again, notice that here the index is n comma 0, and here the index is n minus k minus 1 comma k. So this is the index. So we could have written this term here, e2n0 was right here. This is e2n0, and this is our term e2n minus k minus 1 comma k. So again, notice that this is page k plus 1, and before k plus 1 the arrow was really short, so that's why nothing changed from page 2 to page k plus 1. Arrows went in from 0 to hn b to 0, so this remained same, and on page k plus 1 you have the action. So now recall that, say if you have a sequence like this, say you have a chain complex like this, and you have some map, say D here, so then the homology of this is just kernel of D co-kernel of D 0. So now we take the homology of this. So once you take homology of this, you land in page k plus 2. So once you land in page k plus 2, again you will have everything same, because now the arrow will overshoot it. So from k plus 2 to e infinity you will have the same thing. So again, I'm just going to copy this thing right here. So this has been copied. Then you take the kernel of this map, which will be the homology which you will put here, and you take the co-kernel of this map, which is the homology you put right here, because you have to take the homology of this. So you get page k plus 2. But as you can see, k plus 2 is same as e infinity, because the arrows are now going to be really long. So arrows will go from here to here, which will land in 0 and come from 0. So after this page k plus 2, everything will be constant. So therefore we are just putting e infinity n comma 0 now. So this is page k plus 2, which is also same as page infinity. But we already know that page infinity gives us the homology of the total space X. So hn of X is precisely the components which lie in the anti-diagonal. So sum of these two components is n. Everywhere else there are 0 on this diagonal, except now here you will have e infinity, which will be n minus k comma k. So sum of these two indices is again n. So we are taking this anti-diagonal here. Everywhere is 0, so except in row 0 and row k, our action rows. So our hnx is n plus 0 is n minus k plus k is n again. So this is whatever the entry here is, this direct sum with our entry here. Okay, so what about n minus 1? Again, n minus 1 plus 0 is n minus 1, so this will be it, and this is the anti-diagonal. Everywhere else we have 0. So now you have these two things. So n minus k minus 1 plus k will again give you n minus 1 here. So similarly you have hn minus 1 of our space, total space X. You have e infinity n minus 1 comma 0, and you direct sum with our this thing here, n minus k minus 1 comma k. So this we will write as a sequence. So now we have this thing. This we rewrite as a sequence like this, goes to e infinity n comma 0 and comes from here. So this, and the second portion, this we rewrite as a sequence here. So this is hn minus 1 x. This term you're writing right here. This term we are writing right here. So nothing much. Now you can splice this sequence. Say this is sequence A with this sequence B. So now notice you have this map, and if you splice these two sequences, you get this sequence. So let us see how this comes. So first focus on this map. This map we copy as such right here. So now you have E infinity n comma 0 here. So look at this E infinity n comma 0. So in this comes Hnx. So in this we will have Hnx coming in. So I'm going to copy this right here, and into this comes this Hnx. So this is Hnx. Now composition of this map and this map, so composition of 1 and 2 will give you this arrow, and this is precisely this arrow here. So you get this. So this is our Gysin sequence. And now look at this term here. So this term you can find it right here. From this terms comes out Hn minus 1x. So you write Hn minus 1x. So now compose this arrow with this arrow. You get this arrow. And this is the arrow which we copy right here. So you get a Gysin sequence. It relates space x and b when the fiber of the space is a sphere Sk. So you have this map like this. This will imply that you have this homology sequence like this. You go from Hnx to Hnb. Once you go to b, your homology decreases by n minus k minus 1. Then you go to b, then again Hn minus 1x. Then you go to Hn minus 1b. Again you decrease it by, every time you decrease by k plus 1 when you have these maps b. So this is the Gysin sequence. And you can see this was just an easy application of or easy corollary of Serre spectral sequence.